Hello, welcome to this video on large language model where we will be focusing on embedding. We'll start our journey with static embedding and then subsequently we'll understand positional embedding as well. Now, the purpose of this video is to go through the ideas and concepts how model understand language, human language. We'll go through the intuition and concepts behind these building blocks of embeddings, which are very high dimensional vector space. We'll understand how we are training these embedding vectors by bringing a different word, its semantic meaning, its relationship among different words, and how we train them so that later when we use in language model or different applications of NLP, these embedding vectors plays a vital role. We'll cover few well-known models and how they train these static embedding vectors. We'll cover some applications of these static embedding vectors. After that, we'll start coding demo with one very exciting dataset that I'll show how to download, and then subsequently start working on the dataset to build static token embedding. After that, we'll understand that static token embedding has certain limitation. And that's where comes positional embedding and subsequently contextual embedding. We'll cover positional embedding in this video in depth. We'll understand what are the different mechanisms to build positional embedding. We'll visually see how static embedding is combined with positional embedding to build combined embedding. And then these embeddings are used subsequently in attention mechanism and transformer architectures that we'll go through in upcoming videos. So what are you waiting for? Let's get started. Suppose you see this sentence, or maybe this one, or maybe this one. So unless and until you know these languages, you won't understand anything. First one was in Bengali, second in Hindi, and third one is simplified Chinese. All of them conveying more or less similar meaning. And it is like this. LLM sees words as mere sequences of characters. Just the way, if you are not familiar with any of the below three languages, you will also see them as just sequence of characters and won't understand anything about its inherent meaning or how the sentence is constructed. What is the relationship between different words? So similarly, when we are trying to train LLM, first thing it requires is numerical representation. Why? Because LLM need to convert words into numerical vector so they can process language mathematically. Underneath all this algorithm, mathematics plays the vital role. Thus, first step is to convert them into numerical representation. And if you remember from last video, we started their journey through tokenization process. Now, once it is converted into numerical representation, most important thing for it is to understand semantic meaning. Now, when I'm saying understand, it's not necessarily machine or algorithm really understand them, but we have to give them the mechanism so that they grasp the meaning of words and their relationships to understand what's being communicated. So we have to find a way to tell these algorithms or these models that this is the meaning of this particular word, or some of these words are meaning almost similar thing. Next thing that would be required for this model is to understand syntactic representation. LLM need to recognize the structure of sentence to interpret grammar and word orders. We'll see many examples as we go along that same word may mean different thing in different context, and that's why context awareness is extremely important. In this video, we'll mostly focus on first two things, numerical representation and understanding semantic meaning, while we'll set the context of why context awareness plays such important role in modern LLM. Now, let's again go back to numerical representation. In last tutorial, we talked about tokenization. It's the starting point to convert part of words into token and then assign a token ID. We have seen various tokenization strategies like character tokenization. We have seen simple concept like white space tokenization. Word tokenization, sentence tokenization, BPE, and few more ideas of tokenization, encapsulating how to handle unknown or unseen words, how to handle different punctuation, capitalization, all these things we have seen in previous video. Now, in this video, the focus is on how LLM would understand language. First thing, it requires numerical representation, and that's where tokenization came into picture. But tokenization and assigning token ID numbers is not enough, as machines don't understand words like cat or dog directly. Embedding map these words or larger pieces of text into a mathematical space where similar meanings are placed closer together. For example, cat and dog might be near each other because they are both animals, while cat and toy would be further apart. These vectors are static because once trained, they don't change, even if the word appears in different context. So in this tutorial, we'll be using the term static embedding and not word embedding or token embedding, because this idea reinforces the concept among various embedding mechanisms. Now, for the static embedding, first thing is to convert token ID into dense vector. So if you take example of few words like cat, dog, plum, apple, good, bad, toy, based on vocabulary, we'll assign some token ID to these words. It's based on the tokenization that we are going to use. So once these token IDs are assigned, next step would be to convert these tokens into dense vector in very high dimensional space. And why? Because to translate human language into vectors in high dimensional space that machine can understand and process efficiently. So if you take the example of these 7 words, here I'm showing just 4-dimensional vector, but it could be very high dimensional depending on the algorithm or the size of models that being used. So the dense vector that each model ultimately will be using is in the size of vocabulary size times static embedding dimension. So in case of globe 6 billion vector, it was like 40,000 times 300. So 40,000 was the vocabulary size and static embedding vector dimension was 300. Now let's understand why this static embedding high dimension is required. Ultimately, these vectors are storing semantic information and they also learn word relationship. So how it stores semantic meaning. You can think like every dimension is encoding or embedding some semantic representation and some relationship between different words. In this example, we are showing 4 dimensions and each represent one specific concept or ideas or semantic meaning. So first case, it could be animacy. Then later, it could be the next one could be positivity. The third dimension could be edibility, and the next one would be, suppose, playfulness. Again, these are just for explanation purpose. Actual model will assign these vectors based on different training mechanism, and it might not be easy sometimes to even understand what are the rationale or logic behind each dimension. But at a very high level, from an intuition perspective, we can think like each of them assigning a particular dimension with a specific meaning. So here, if you think the first column of the vector, which is talking about animacy, in this case, cat and dog both are assigned 1 because they are living animals, while orange, apple, toy, all these are assigned minus 0.5 because these are non-living objects or food. And model has presumably assigned 0 for good and bad because they are neither animal nor anything, because these are like a abstract adjective. Similarly, if you take it, the last one, the playfulness, the fourth column in the vector, you can see the toy is assigned 1, dog is assigned 0.7, while cat is assigned 0.5. Usually, dog will be more playful compared to cat. That's why the model assigned like that. Now, let's see this in a visual representation for all these words. So, first, token ID is assigned, and then we are converting this token ID into static embedding. Now, it will be very interesting to see all these values in a vector space visualization. Here, we are showing it in 2-dimensional vector space, but again, since these are very high dimensional vector space, it may be difficult to even visualize. But from 2 dimensions perspective, we can think all these vectors are pointing to some dimension in the vector space. And as you can see that for animacity, the dog and cat sitting together, for edibility, apple and plum sitting together, for positivity, good and bad sitting in the opposite part of it. And as we said, toy is like 1 for playfulness, while dog would be 0.7 and cat is like 0.5. Now, if you can see all together, these are the way these vectors are represented in a very high dimensional vector space, retaining the semantic meaning and coming close together for similar kind of words. What are the different types of these static embedding methods? We will go through 3 of them. First one is globe. The inherent idea is like we are teaching which word usually appear near each other. We'll see that word co-occurrence and vector optimization plays the vital role in globe algorithm for static embedding. The next well-known word embedding is word-to-vec. So in this case, we show the machine examples of words used in sentences. It uses local context, words around the target, and there are 2 flavors of word-to-vec algorithms, and we will go through both of them. Third one is about breaking the words into smaller parts and explain those. It brings in subword information for better handling of unseen words. This is called FastText. So there are many other algorithms, but we'll limit our this video only focusing on these three to share the ideas how those were trained. So now let's take a look at Glove. What it does? What is the big idea behind it? Glove makes word vector closer, and it looks at how often words appear together in a large collection of text, like a giant book or many websites. And then it tries to create vectors so that words that appear together a lot have vectors that are close to each other. So fundamentally, a co-occurrence matrix is built which counts how often words appear near each other. This matrix is then simplified into dense vector using gradient descent or similar algorithms. The model optimizes those vectors so that words with similar meanings or that often appear together have similar vectors. For example, say we have two sentences. AI improves efficiency. Another one is machine learning boosts efficiency. So here the words AI and machine will have similar vectors because they often appear near efficiency. And that's the concept behind Glove. Next, we'll take a look at word2vec. The first we'll take a look at concept called skipgram. Skipgram tries to predict the word that surround a target word. So what is trying to predict? It's trying to predict surrounding words, and it's using a central word to predict the surrounding words. We'll see another variation of it. So how this is being trained? It trains a small neural networks to do this prediction. It predicts context word from a target word within a window. Maximum positive context probability for those which are coming within that window, and minimizing random negatives. It assigns some random words and negative contrasting methodology it does to assign the probability or likelihood using sigmoid laws. The vector it learns in this process are the word embeddings. So suppose you have a sentence, user tweets about AI. So here, if we use a sliding window around tweets, so there is user and about AI. So in this case, we will be training this central word tweets and predict. So in this case, AI and user will be positive context and will give some random negative context like pizza and dog. Those are not related to tweets. In this case, the skipgram will try to predict AI or user. So all those words will be nearer in vector space. Now, second concept is just the opposite one in case of word2vec. Here the method is called continuous bag of words. In this method, it predicts a center word from surrounding words. So in skipgram, it was predicting surrounding words from center word, and here is the reverse, predict a center word from surrounding words. Here, how it works? It trains a small neural network to do the prediction. It predicts targets from context average. So for example, if we have a sentence, say user, and there's a blank about AI. So based on the corpus or example during the training process, it will learn that the blank would be say tweets or posts. And that's how it will put tweets and posts somewhere near in the vector space. Next, we'll talk about FastText. Now, what is the key idea behind it? It breaks down words into smaller pieces called subwords, but inherently, it's like word to vec only. So it splits the words into smaller chunks, and vectors are trained for those subwords using a similar technique like a skipgram approach. The final vector is computed by adding all these subwords. One example could be hashtag. The word it might not have seen earlier, but since it's breaking into subwords like HA or has or hash and tag, it can combine all this knowledge together while computing the vector, and that's how, even though it is not seen, it will be able to relate and understand where the vector representation would be placed. So ultimately, this FastText is extending the idea of word to vec algorithm, and its strength lies in the fact that it can efficiently handle unseen words. Now, let's take a quick look at all these different approaches and what are the difference between them, what are its strength, and in simple terminology, what they are. So GLOVE is a co-occurrence matrix based, and it's basically counting the global co-occurrences. It captures global patterns, and you can think it's like a word social network. Skipgram is like predicting context from word, and it's good for rare words. It's like a guessing friends from a person. SIBO, it's predict word from the context, the opposite of skipgram. Its strength is faster, smoother vectors. In a way, you can think of it's like a guessing missing piece from surroundings. And FastText, it's using character anagrams, handles unseen words very efficiently. And you can think of it's like understanding words from their parts. Now, in terms of static embedding, why we are saying static embedding is really important. Semantic understanding, as we can see from this high dimensional vector and visual representation, that they encode semantic meaning in vector space, bringing the meaningful or similar words together. Now, what are the other aspects of this static embedding? Faster training. Pre-trained embedding speed up learning and reduce data requirements. A lower computation. Pre-computed vectors cut down on training cost and memory usage. Vocabulary consistency. Fixed embedding ensure stable and representations of words across tasks. Interpretability. We can visualize and even do word math, like famous one, king minus man plus woman equals queen. So there is no black magic, it's pure mathematics, and it's the vector space computation that's giving this interpretation or reasoning. Transfer learning. Reuse embeddings for new tasks or low data scenarios. We'll go through static embedding applications. Semantic search, enhancing search accuracy like Google's RankBrain. Retrieval augmented generation, RAG. Blending search with text generation. Multimodal AI. Connecting text with images, audio, and video like Clip and DALL-E. Conversational AI, enabling chatbots and virtual assistants. Text classification, automatically categorizing documents and context. Named entity recognition, NER, identifying people, places, and entities in text. Sentiment analysis, detecting emotions and opinions in language. Machine translation, translating text across languages. Text summarization, condensing long documents into key points. Question answering, extracting direct answers from text like chatbot, and many more. I'll be using Rabindranath Tagore's writing for preparing data for training LLM. Rabindranath Tagore was a famous Bengali polymath. We'll be using his work, particularly stories, which is compiled in Project Gutenberg ebook. We'll be downloading these stories from Tagore, and then we'll tokenize them first, then we'll create static embedding from these data, and then subsequently we'll build the training pipeline for LLM as we go along. First step will be to download the work of Rabindranath Tagore and pre-process text. For that, I'll be using Beautiful Soup, and these are the libraries that I will import first. We'll be using OS, we'll use requests and zip file, and from BS4 we'll import Beautiful Soup. Now, my idea is to build a function for each major activity that we'll be doing with this demo code. Though it's a toy representation, but if we build these functions later, we can extend and reuse them for various purposes. So first, what I'm going to create is a function where we'll be downloading and pre-processing text. We'll be giving the URL and then we'll store it in a local file. In this function, what we are doing, we are first checking the download path, not there, then we'll start downloading this file from the given URL, and then we'll start writing in the local file. So the way this is created, because we might have to run the code again and again, once it's downloaded, we should not try to download again, rather we should use it from local file. This is the code here. If it doesn't exist, it will download, otherwise it will show the file already exists. Then what we will do is we will open the file, downloaded file, in read mode. We'll be using encoding UTF-8 so that it can capture many characters which may be not possible with ASCII or other encoding mechanism. So Beautiful Soup will parse this file, which is in HTML, and store it as a plain text. And this function finally will return text file. Now to test it, what we'll do, next step, I'll be using our simple sentence to test various steps in this demo. So first, we'll be printing this simple sentence, and then as part of step 1 execution, we'll be pulling the file from Gutenberg for the Tagore's short stories, and then we'll be storing it in the local file. Then we'll sample first 1000 character from that text file. So let's run this. So this is the simple sentence. She plays the piano well that we'll be using. And this is the text file that is downloaded from Gutenberg. And if you see, these are the first few lines from basically first 1000 characters. At this stage, we have our sample text data. Now, next step is to tokenize this text. And for that, we'll be using BPE tokenizer. So from tokenizers library, we'll be importing tokenizer. Tokenizers.model, we'll be using importing BPE. We'll be using the trainers, BPE trainer, and pre-tokenizers will be using whitespace. We are not using byte level encoder, but rather character level encoding. That's why it's whitespace. Now, as I mentioned, every step we'll be creating function so that we can reuse it. So in this case, we'll be defining a function called train tokenizer. So the purpose of that will be once text is given, it will return a tokenized data. So you see tokenizer and the tokens. So it will return what is the tokens tokenized from given text. Here we'll be initializing BPE tokenizer with all the unknown tokens will be given this UNK. We'll set our vocabulary size 500 and we'll also use some special tokens like unknown, CLS, separator for SAP, padding, mask, all these we'll be using. After that, we are using the pre-tokenizer, which is white space, and then we'll split text into sentences for training. So all the text will be split into sentences. And then we'll use the train from iterator, the tokenizer. This is a standard library and we'll just use that to tokenize our text. So once the full text is tokenized, it will give the tokenized data and that's what it's returning. So let's run this step. So in step 2 execution, what we'll give is the Gutenberg text that we have downloaded. We'll give it into train tokenizer and it will create the tokenizer and tokens. So if you see, the number of tokens processed from the dataset is 109604. Let's take a look at the tokens for the sample data. And you can see this is broken like this. So all these are individual tokens based on BPE. Now, third step would be to use an existing token embedding. For that, we'll be using globe 6 billion tokens with 50 dimension. So here we are creating two functions, one for downloading globe embedding and the next one will be to load globe embeddings. So this is again, if the file already exists in our local, we won't do anything. Otherwise, it will download the data and it will store so that later we can use this data for static embedding. So the next function we are building is load globe embedding. What it is doing is it's going by each token and then it's also putting the corresponding embedding for the token. So now let's run this tab and to here I have already downloaded it few times. That's why it shows already exists locally and then its total globe embeddings loaded is 400000. So this many numbers embeddings are loaded from this dataset. So next step would be to convert the tokens to static globe embeddings. So here we'll have two steps. In first step, we'll get the embedding and in the next step, we'll convert tokens to embeddings. So here, if you see the arguments are token, globe embedding and embedding dimension, it returns a NumPy n-dimensional array of embedding vectors for the token. Later, we'll use that array and convert each one into corresponding embeddings. So once we create this, next step would be to run this. For later processing purpose, we'll be defining some constants for training. Context length, we are using 10. This is the context window. Batch size is 4. Later, we'll be using mini batch for processing. And embedding dimension is 50. This is the globe 50 dimensional embeddings that we are using. So first we'll demonstrate by running this on sample sentence. Here we are calling the tokenizer to encode and give the tokens. Later, we'll show the static embedding for this simple sentence, how it looks like. We'll show only 6 dimensions out of the 50 dimensions. So here it looks like we are converting these tokens. And if you see static embedding for she is like this based on the globe, PL like this, AY like this, and so on. Now we'll apply this for entire data set. So you can see the first 5 tokens in the downloaded data set the project Gutenberg, all these are basically embeddings of first 6 dimension. That's all for creating embedding from tokens, that static embedding. Later we'll see positional embedding and how they are combined together. While static embedding brought revolution in the field of NLP and it's extremely important in LLM training pipeline, it still has two limitations. It's not aware of context and it does not capture position of the token. Now, context we'll cover in next video when we share the idea behind attention mechanism and various concept and architectural consideration for transformer architecture. So, one is context, other important part is position of the token. We'll see transformer is trained in parallel. All these LLM models, whether it's using transformer encoder or decoder or both, or some variation of these architectures, all are trained in parallel. Thus, it's really important that when we feed data into these models for training, they are aware of position of each of these tokens. Now, let me give one example which will make things crystal clear. Suppose we have a sentence, she plays the piano well. Another one could be, the lead role she plays brilliantly. Third one, chess he plays with great skill. Under tension, the row plays freely. Another one could be, in silence, she plays her part. So you can see the same word plays have different meaning in different sentence. First one, it is talking about music, performing music. Second one, it talks about perform or acts in a theatrical role. Third one is talking about playing a game. Fourth one about flexibility or moves. Fifth one is talking about role or duty. Again, you can see that position of this place is different in this sentence. First one it was second one it was fifth, then third, fourth. So there are a lot of variations. So if you put them, you can see that same token and having same token ID has different position. So all these examples, positions are like either in first position, or it may be in fourth position, or it may be in second position. So we have different variation of same words. So while static embedding makes sure it's the same representation, but we have to somehow tell the model that position is different. And that's where the positional embedding comes in. Now, let's take a look at positional embedding. First of all, why do you need positional embedding? It serves two purposes. One, capture token order, and the second one is enable sequence understanding. The main background is transformers or other LLM models process all tokens in sequence and also simultaneously using self-attention. That's why inherently those are order agnostic. Positional embeddings provide a mechanism to inject the positional information, that is the order of tokens, into the model. And sequence understandings without positional information, like for our sentence, she plays the piano, and say another sentence, the piano plays she, would be treated identically by a transformer or equivalent model, leading to incorrect interpretations. That's why positional embedding ensures the model understands the sequence order. You can think about the intuition is positional embedding is providing positional signal. It's also providing geometric interpretation. Like positional embedding as coordinates in a high dimensional space that shift a token's embedding based on its position, preserving order while maintaining semantic meaning. And it's also compatible with token embeddings. That's why positional embeddings are typically same dimensional as token embedding, and we'll be adding directly with token embedding or static embedding to derive the combined embedding representation. Now, the combined embedding that we will be using is static embedding plus positional embedding. Let's take few example of positional embedding implementations. The first one that was introduced in original transformer paper was based on sinusoidal positional embedding. What it does, it uses fixed sine and cosine fractions to generate positional embedding. So our example, she plays the piano well. Here, all these are tokens and these are the positions of the tokens starting from 0, 1, 2. Place here is position 2. Now, this paper shares how these positional embeddings are calculated. So if you just take the example of place, you can see how the calculation will come, and these are the numbers being derived. So the embedding vector would be like this, and we will see this in our visualization later. Now, there are other mechanisms. One is called learned positional embeddings. These are adopted in BERT and GPT models. These treat positional embedding as learnable parameters. So those are trained during the training process of these models. Another idea is rotary positional embeddings. It's apply a rotation to the token embeddings based on their position, encoding relative positional information. There is another idea which is relative positional embeddings. It was introduced for transformer XL models. It's use relative distance between the tokens instead of absolute positions. Now, let's take a look at how this positional embedding and static embedding are combined together to derive the final combined embedding. So if we check the overall flow of token embedding, starting with static embedding followed by positional embedding. So let's just go through the example of she plays the piano well, this sentence. First, we'll be converting all these tokens and assign token IDs. Next, again, we have token position. In this case, we are using CLS and dot, all these as tokens as well. So in static embedding, it's assigning high dimensional vectors. In positional embedding, we'll have the position encoding done. And the later in the combined embedding, what will happen for each of this, it will be adding them and then put as a combined embedding. So what we have seen that if we add the vectors from static embedding and positional embedding put together, then it will be ready for feed into transformer architecture, where it will be further fine-tuned and it will be using context on top of it. So as you can see here, when we go through the coding, what it will do, it will take each element from static embedding and then positional embedding, then it will add them together and create a combined embedding. Here we have clipped the values between 1 and -1, but in practice, there are different approaches to handle once we add these numbers. So that's how the combined embedding looks like. Now we'll demonstrate positional embeddings. So for that, we'll be creating positional encoding. Here we are using the sinusoidal positional encoding mechanism. So you can see based on positions, if it is odd or even, I'll be using either sine or cosine. And then it follows the calculation that was used in transformer paper. We run this, and in the next step, we'll see how the positional embedding looks like for sample sentence. So for sample sentence, position 1, 2, 3, how it looks like, and these are the positional encoding values. Now what we'll do is we'll add this value into static embedding. How it is effective that we add the values that we have seen. So after adding, so this is the combined embeddings, static plus positional for sample sentence. So you see, she play all these tokens. This is the combined embedding after applying both static and positional embedding. Now we apply it to full dataset, and we'll see how it's applying. Here we have first 5 tokens, and this is how the combined embedding is applied on them. So that's all for this demo. All these codes will be available in the GitHub repository. You can always take a look, and if you have any suggestion, do let me know. I think it's important to understand a little bit about vector database before we wind up this video. There are different types of embedding models. So far we have gone through text-based embedding models. There are embedding models possible for audio, video, and many other types. So embedding models create vector embedding. Those embeddings are now stored in specialized database called vector database. Later, these databases are queried to extract relevant information when needed. There are many well-known vector databases in the market like Pinecone, Chroma, Milvus, Zilis, Vespa, Weaviate, and many more. In fact, some of the traditional databases now offering vector database as well, like Redis. Now, 2 aspects of vector database is very important. One is indexing. So that's how it stores the data so that it can be searched very efficiently. There are many well-known mechanisms to index those databases. Some of them are approximate near neighbor or ANN algorithms. It has got HNSW like hierarchical, navigable, small world. Then IVF, LSH, PQ. PQ stands for product quantization. There are tree-based indexing, KD tree, which is k-dimensional tree, ball tree. There are also many graph-based indexing mechanism available. Now, while indexing is the core part of how the data is being stored, the main usage of this vector database is how the search is done. So primarily it does similarity search. There are different mechanisms to extract similar data like cosine similarity, Euclidean distance, dot product, checkered similarity, Hamming distance, Manhattan distance, approximate nearest neighbor, ANN search, and many more. And from use case point of view, while semantic search is the most prominent one, there are other uses like recommendation system, video and image search, anomaly detection, RAG. Nowadays, RAG has become extremely important in chatbot, where it extracts relevant information, and those informations are stored in vector database. Multimodal search, duplicate detection, clustering, etc. So with that, we have come to the end of this video. Now a quick recap what we have gone through so far in this video. We have covered what LLM need to understand natural language. We have talked about token embeddings, understanding static embeddings. We shared concept, intuition, and vector space insights for static embedding. We shared key ideas behind prominent static vector embedding models. We shared coding demo about creating static embedding from training data. Then we shared the limitations of static embedding and why context and position plays a critical part in this LLM training pipeline. We spoke about positional embedding concepts and how it is integrated with static embedding to create the combined embedding. Then finally, we have shown code demo for merging static and positional embeddings. That's all for this video. In next video, we'll be covering attention mechanism and various aspects of transformer architecture.